Yeah, thanks for the time. It's very good today. We have the first TILOS seminar of the fall semester. We have Michael Galkin from Intel Research Lab here, Intel AI Lab locally in San Diego. Michael is in the University of Bonn in Germany. And after that, he also spent some time briefly in Milan, Montreal, which is one of the standards research nowadays. And before he joined Intel Research earlier this year. And so he has very broad interest in graph representation learning and also geometric deep learning. And recently he has also put a lot of emphasis in looking at AI for science. And let's welcome him, and we look forward to your talk.
Thank you. Thanks, Professor. Yeah, generally, thank you for inviting, and that was a nice meeting first at the TILOS, and then we arranged the talk. Yeah, so hello, I'm Michael. I am coming from Montreal, moved recently from Canada here in January. I was doing my postdoc there on graph learning, and until I'm a research scientist working on mostly graph learning. I sometimes write in some writing on graph learning, and I quote Michael Bronstein and sure nice thing also. At least now he has an artifact, but then we'll call it 4 Michaels. I see. Yeah, so I'll be talking about graph foundation models, and to define this thing first, what is the foundation model, where they are all the rich in language domain. So generally we'll think of it as some single pre-trained model, training some self-supervisation on some pretty generic task, and then it can be applicable to any downstream task, being a zero-shot learning or fine-tuning with some in-context learning, how it's fancy to say those days. Generally, we want, yeah, I can close this. So yeah, if we what about foundation models? There are certain features for them. At first, we want them large because LLMs are large, and we know that there are some emerging properties, so we want them large. However, for each of those features, there are some caveats. So, for large models as large as LLMs, we actually don't know the scaling for graph models, right? So those are all ongoing challenges, and they're pretty generic for different domains. So yeah, for large models, we actually don't know if there is a strong signal that graph models benefit from scale. Then if we talk about some self-supervised objective that you want to train, like next token prediction, what is next token prediction? Because our domain is so wide that it's hard to devise such a pretty generic as next token prediction task. So we talk about geometric models probably with some doubt energy. We talk about some social networks, will be some maybe graph reconstruction objective. And L1 for all uniform featureizer means that you can stuff everything into tokens. The images can all be tokens, audio into tokens, and something else. You don't need symbols anymore. You can even use byte encoding right now. So such uniform featureizing is also missing graph models, simply because if you have, say, 3D geometric graph, then you would also have some 3D features of atoms or some other structure that you're modeling, which do not exist in social nets. So that's quite some discrepancy that presents some problem for building graph foundation models. And talking about them, what we do at Intel with them. So far, focusing on 2 big areas. Will be knowledge graph reasoning. So this is more of a hardcore reasoning on very large graphs. We'd like to inference on any domain. And the second one will be AI for science. There will be 2 parts of the talk, and I'll make some small pause after the first one. Yeah, so 2 main focuses I'll be talking today. It's knowledge graph reasoning and AI for science. So we'll be making one stop after each part. And so AI for science, those are mostly molecules, proteins, materials, perhaps more even materials and crystal structures, and with some particular focus on generation of new theoretic structures. Yeah, so starting with foundation models for graph reasoning. So I first explain what is knowledge graph and what we do understand by reasoning, and what's the bigger problem why we need foundation models, what's the problem actually getting those. So knowledge graphs are pretty much everywhere. If you're using them, if you use internet every time, you probably already stumble upon them somehow. So the graphs behind Google and Bing, those are knowledge graphs, and they usually give those nice info boxes. Usually this is structured information that they store in some huge graph. There are rumors that Google KG contains something like 500 billion facts now, maybe close to 1 trillion at those days. So those are more encyclopedia knowledge that is also partly accessible in Wikidata. Freebase is dead, but Wikidata is perhaps the most well-known public graph that sends info boxes to Wikipedia. So if you ever use Wikipedia and you look at those factual information, the information comes from Wikidata, in fact. And those kind of encyclopedias are used in retrieval augmented models, so pretty much everywhere. And if you want to improve factual consistency of LLMs, you would use those kind of encyclopedia graphs. Then there are scientific graphs, like UniProt, for instance, on which a lot of protein models are trained, like all those protein LLMs, AlphaFold. Taking data from UniProt, UniProt is, in fact, has a graph representation as well. And there are a lot of drug-related combined graphs like DrugBank and PageUnit and so on. So they cover this domain as well. And then there is also a bunch of very domain-specific graphs. Like I recently stumbled upon this spatiotemporal urban KG, and that one describes in graph form road networks in Chicago and New York. So that they still have interesting tasks on top of that, and it's still actually a multi-relational graph. So there are thousands of those domain-specific graphs. All of them have their own specific vocabulary. Like spatiotemporal probably talk about location and some routes and some other road properties, while encyclopedias, they will tell you about basic encyclopedia, who was born there, whose parents was there. And generally they have non-overlapping vocabularies. So they have different relations and different entities. And that's the problem we'll try to break. So in the basic setup, those knowledge graphs are relational graphs. They are directed graphs. We have explicit edge types. So R1, R3, those are R7, those are all discrete edge types. We expect node features are not given. Usually for some graph tasks, you would say, okay, we'll have some initial node representations. Here we actually say historically that we don't have them because not many of them have textual representations. Some have data type representations, some numbers, but normalizing them is a big mess because for instance, only 10% of people in Wikidata have their dates of birth, and others do not. So what do you do? You will have, most of them will have NA or something else. Some nonsense. So yeah, the basic is that input node features are not there, and there are several setups: transductive and inductive. That transductive means that you run inference on the graph you trained on, and inductive means that you would run inference on some completely different graph. And of course, if your graph is completely different in terms of relations, then it will be inductive inference. And by reasoning, we would understand a pretty simple objective that given the starting node and some relation type, want to build a distribution again over all nodes in the graph and answer what would be the possible answer. So we are ranking all of them in the graph and trying to predict the one which looks most probable as the tail of this triple. So that will be a knowledge graph conclusion. And by inductive reasoning, we understand that at some point we might be given a new node or completely new graph with new relations or graph with new nodes, and we want to perform the same task, but now the nodes are new. So again, we don't have any feature in them. So that's the main problem, how to do some featureizing. Looking at some brief history, how this reasoning was solved before. So the area is already pretty old, started from 2011 with first models doing some tensor decompositions. They were historically transductive only. So you would build some huge embedding matrices for all nodes and the relation types. If you have 1 million nodes, you have a huge embedding table and then dot embedding of 1 million rows. That's would be quite resource consuming. And after that, there has been like hundreds of KG embedding models. I actually stopped counting them already after maybe 2015, 16. It was way too much. And there has not been substantial progress already for several years. So if you look at some benchmarks, all those performance of those embedding models is stale, and it's not really improving. The problem is that those are graph-specific embedding models, so they are not transferable. We have to retrain it for every graph, and they have big internal limitations. And the first step towards making them somehow inductive was with geometric learning. Geometric EL appearing around 2017-18. That gave us a lot of math and some tools to work with graph structure in general. And the breakthrough there after 2018 was neural Bell-Ford. So that's a little hidden by Zoom. So this is called the neural Bell-Ford net, NBF net, so published with Neuros 21. And this is one of the papers that is now pretty classical, I would say, in the literature. So it introduced the concept of labeling trick and relative representations. So instead of learning now all those entity and relation embeddings, what we will do is we actually use, we don't need entity representation anymore. We only fix only the relation representations, and we would use node labeling, which means that given a starting node, this will be here the blue one here. We would label it with some learnable vector. Then we do then run message passing, and then all other representations we have, they are relative compared to the starting node. And since we only learn edge types representations, we can transfer to any graph that shares the same set of relations. So if you have, say, Wikidata, a graph with Wikidata relations, you can still work on new Wikidata entities that share the same set of relations. So yeah, NBFNet 2021, fixed relation types. And we're still in the quest of finding a model that can generalize to completely new graphs at all, even with new relation types. And in general, it might look as hard as generalizing to completely bigger graphs. So freebase is a pretty standard graph, which was the origin of Google KG back in like 15 years ago. But the latest DAM has something like 90 million nodes, a few thousand relations. And the Wikidata is the largest graph so far. It has also 100 million nodes, so different relations. So learning shell embedding for them is pretty useless. It will take like maybe terabyte of memory, and it won't be transferable. So you training a model on Freebase, you won't be able to run inference on Wikidata. So it's very much like waste of compute. We don't want that. We want something that is transferable. Transferable that you can pre-train on one and run on another. And the main problem there is you have different vocabs. And knowing from that geometric learning is a quest of learning symmetries and invariances, and finding some invariances, we were thinking, what is the transferable invariance here? What can you learn that will be shared between graphs of even of different relational vocabularies? And there we start from the from existing inductive models, and that learn some relative entity representations by means of this labeling trick. So if you have some graphs say about Michael Jackson, about this code, then by labeling the Michael Jackson node, you get representations relative to Michael Jackson. So you theoretically, conceptually, can put Michael Jackson in the center of coordinates, and everything else will be relative to it. And if you have the same set of relations, say about the graph about Beatles with new entities, then building relative representations to Beatles, you can do the reasoning. So that's how those inductive entity models work. You still the caveat is that you still have to have the same set of relations. And in that recent work that we recently created and just in archive for a few days, we found that you can use actually the relative relation representations. So if you start from the graph of relations, then there are some invariances. So it's a bit messy. I can go into detail first. So given the original graph, first build graph of relations. So from Michael Jackson disco, we have some relation like author, genre, and collab. And we can actually, using some sparse matrix multiplications, very few of them, we can build a graph of relations. For instance, we know that Michael Jackson authored Thriller, and Thriller is of genre disco. So the tail of authored is the same as head of relation genre. So we can put can I use it? Oh yeah. Then we can use the authored, connect the authored and genre node with a special relation. And those are, we call them fundamental interactions, like tail to head and head to tail. There are actually 4 of them. And those are actually remain the same. So that's a cool observation that whatever relations are in your graph, they still have the same fundamental interactions. So some relations are they have nodes that are heads or tails to something else, and those can be efficiently obtained in linear time, pretty much. Yeah, so let's try to use the graph of relations, and that would lead us to the model that we that we politely called ultra, not pretending at anything at all. So like visually unified, learnable, and transferable representations, and it transfers to graph of new relations. Like here, for instance, our original graph with Michael Jackson about his musical endeavors, and here we graph about Donald Mills and his student and awards. You can see that although everything is different, entities and relations are different, their fundamental interactions are still pretty much the same. So if we now build relative relation representations, they do transfer. So we can infer relative relation representations now by the means of the labeling tree. So how the algorithm works here is that given some relation graph, actually at inference time it can be the same. It can be the same, it can be completely different. The thing is that we're given a graph, we're given a query, so we're always conditioning on some relation. First, we build a graph of relation and use the labeling trick. So by labeling trick, we understand that we use this genre node and we initialize it with some vector. In fact, it's just a vector of ones, so it's not a learnable thing. We found that learnable doesn't transfer. So just put vector of all ones there. Everything else will be zeros, and they are just run the message passing procedure. You'll get unique representations, all relation representations relative to this starting relation. So the nodes in this graph are in fact unique relations from the original graph. And a cool fact is that for each relation we have a unique set of relation tensor. So if you have, it means that for genre we'll have one tensor of size r by d. If you for collab relation we'll have another tensor of r by d, because if you initialize it and we use a labeling trick and run the message passing, then the final representations will be different, and we like that very much. And then having those relation features, you can plug them into any inductive GNN, like neural network for that. And here we have a fully inductive model in that sense. So why does it qualify as a foundation model? Because we don't need any features. So it's a universal featureizer per se. If you have some textual features, sure, do torch cat, it will work. There aren't many learnable parameters, so we only talk about those 4 fundamental interactions and some GNN weight. It can generalize to absolutely any graph. So that was, I'll talk about it more. But since it's all those steps are non-parametric functions, so you can apply it to any already, and you can run the zero-shot inference of a pre-trained model. Also, or do the fine-tuning. So it literally transfers to anything. So that is the main experiment. We trained it on 3 standard graphs in the literature, which will be mostly encyclopedia-like graphs of the size of 10 to 40,000 nodes. And we run the inference on 60 other graphs, which come from different graphs, like from Freebase, from Wikidata, some now, and some other domain-specific or other big graphs like ConceptNet, Wikipedia, and Yahoo, and so on. And what we observe is that the zero-shot model, so that's perhaps the most important point here in this image, that on average, the zero-shot performance beats a lot of those supervisedly trained embedding models. In many cases, the current state of the art are still those old embedding models. And they are trained end-to-end on each of those graphs. And here we say, cool, we have just one graph, and in the zero-shot mode, it beats most of them without seeing this graph, without training it at all. And if you do some fine-tuning, then it bumps the performance about 10%, even more. Cool features that it generalizes to different sizes, which is a common problem for GNNs, in fact. So usually you have some size generalization issues, but here we found that it generalizes equally well to graphs from 1,000 nodes to 100,000 nodes. It's like a graph of 2,000 edges to 1 million edges. That's a pretty cool result. We actually don't know why it happens, so it's still a theoretical question. Looking at some numbers, we see that the pre-training performance, if you still jointly pre-train all those graphs, is still slightly worse than existing state of the art. but it generalizes so much better. And if you look at the total average across all those graphs, then the performance is significantly better. We have all the numbers there in the paper, but generally it is significantly better. And how it generalizes to new unseen domains, it's actually the main question from the very first slide. So we trained it on encyclopedia graphs. How well does it transfer to other domains? And for instance, the graph from combined graph talking about biology and drugs. And we say that with zero-shot performance, it works as well as the model as you train on scratch from this predictive graph. If you fine-tune it, then it beats that state-of-the-art by a large margin. You can also try doing some common sense reasoning with ConceptNet, and it's a weird sparse graph, but it's still not bad after fine-tuning. And in those, say, geography, spatial temporal graph, it, again, from the zero-shot performance, the graph you just feed into a pre-trained model is already better. If you fine-tune it, it becomes all state-of-the-art gets behind by a good margin. Actually, I think we exhausted pretty much all existing multi-relational graph datasets of this size. So if you know any more, let us know. 60 something we collected, and I am not aware of those if there are anything else from that. Yeah. So another question: do we observe any benefits from pre-training? How does it compare if we train the model from scratch again on each of those data sets? And the gains are marginal, but they exist. So it means that you can save a ton of compute by just running the inference of one single pre-trained model instead of training it every time on each of the data set. And that would, yeah, depending on the graph, so on the size of the graph, number of graphs, you can run one model instead of spending a lot of GPU power on training each of those GNNs. Another question, which slightly touches upon scaling laws, is that how does model benefit if we add more data into the pre-training? Because those graphs are different in topology. Some are sparse, some are dense, some have maybe 20 relations, some have several thousand relations. And the interesting fact here is that so those are numbers on the zero-shot inference, on average zero-shot inference on 40 different graphs. So what we find is that generally, the more graphs included in the pre-training set is the best, but there is some certain saturation point happening after 3 or 4 data sets. This is still a question why it happens, because usually if you say train LLMs, then the more tokens you show, the better, or the longer you train, the better. There are some training tricks. So generally, we're still in the beginning of this journey. So it's still a question. Maybe we should increase the model size to get over the data sets and derive some scaling rules. So that's so generally that's the first sign that perhaps from the showing more data it will perform better. We need to investigate it further. And finishing this up with some big picture, what can be done? That's actually a pretty big area of research. Having foundation model, we can extend it to a bunch of graph level types. So here we only consider simple link prediction, but we have far more interesting complex tasks like logical query answering, or do some node level regression, graph level regression on that, because we now have a universal feature. In terms of settings, you can apply it to different graph modalities or different representations of those graph. You can add features or think whether it works well enough without them. So that's pretty much how I will select my next paper. I just randomly spin this wheel and through the darts, and that will be the topic of next paper. Yeah, and the scaling laws, that's perhaps one the interesting theoretical part, is that we generally see some first signs that the scaling it works better, but for graph models it's notoriously harder than for LLMs because we're not actually not using a transformer here. So yeah, we actually have designed the first foundation model that doesn't use a transformer. Wow. Some open challenges here is that we first would like to derive some scaling laws. The model is pretty small, just 200K parameters. It fits on any GPU. Actually, it's more the problem of the graph that how large is the graph that would imply how hard will be the hardware requirements. We would like to investigate some theoretical properties, because we generally have a feeling that we are entering here the second order logic here, because we have the real graph of relations and so relations without relations. So that's second of logic. We would like to extend it to more complex tasks, which will be pretty straightforward though, or for instance, for logical pure answering. And we would like to finally scale it to graphs of really large graphs of billions of nodes. So that would be the first part of those potential internship projects. So if you were interested in some of them, just pay me. That would be some cool, interesting projects to work on. Yeah, the archive submission is pretty fresh from just appeared finally a few days ago. The checkpoint can run absolutely any graph. And I'll be talking more about this in, I think in 2 weeks at Stanford Graph Learning Workshop. I just learned that we've been selected for a talk there as well. Yeah, so that ends the first part. So if you have any questions about this part, let's discuss it. And I'm also looking at the Zoom chat.
I have a quick question.
Yeah.
So you mentioned that so for knowledge graph, that you use graph transformer-based approach, which you also have a lot of. I mean, is it sensitive to this kind of? Is it actually harder for transformer like architecture to capture this kind of relation?
Yeah, we actually tried the transformer first. Yeah, transformer didn't work that well. Transformer needs better features, and you need more data. So transformers are good when you have ginormous amounts of data. And in the same sense as CNNs, kept comparing CNNs for vision and visual transformers, VITs started to be better when you really feed them a good bunch of data. Here we are working the rather scarce regime, like all those 60 graphs. It's good, but it's not like LLM size large. So some more data efficient models, sample efficient models like GNNs here, they work. So far, graph transformers, we found them actually be inferior. And it's interesting, probably they might not do that well with the labeling trick. So because when you initialize here some starting node with the, say, with 1 and everything is 0, if you do the math, then you might end up, transformers do not like input 0 inputs. Otherwise they can quickly oversmooth everything and it will be 0 as well. So you need some tricks to mitigate zeros as well. Alrighty, then coming to the second part, which would be AI for science applications. That's the second focus, with a lot more physics and math. Those are images from a recent distributional graph former. So there's a recent generative model for different kinds of 3D information for molecules, proteins, and materials. So this one, for instance, is some carbon-based materials with the conditioned on certain properties, and generative models can create those structures, and then we'll build those fancy visualizations to tell people how cool generative models are. So the first, how I started in this area, a little shameless plug and self-promotion, that we started working on graph transformers about 2 years ago, and our first project on that was Graph GPS, general, powerful, and scalable graph transformer. It was our entrance to the field of molecular ML. A graph transformer that combines both MPNNs and transformers, out of which we wrote quite a number of blog posts, and we have implementations of them pretty much everywhere. And it is pretty much the transformer of 2022. Yes. Because we won a lot of challenges with it. We got the state of the art in the biggest molecular regression benchmark, where we PubChem quantum mechanical CQM from OGB, and we got quite strong performance on Zinc. By that time, it was state of the art. Already, like after a year and a half, we have better models, but by that time it was still pretty strong number. And for PCQM for M, I think that is still one of the best state of the art numbers. In terms of parameter efficiency, you see here it compares favorably as well. So yeah, our graph transformer model here got quite some community traction. We like that people use it in other tasks as well. And we extended this work then to some long range graph benchmarking tasks. So that's really fresh benchmark that measures how well those graph models capture long-range interactions. Those long-range tasks can be in partly say in graphs built from images, so from Pascal VOC. Those are if you work in CD, you probably know those datasets. And a few of them were from protein datasets from that we built from peptides and from PCQM. So those are graph level tasks, node level tasks, and also contact map, which we link prediction task. That's like a small kudos to the original KG link prediction thing, because we use the task formulation here is the same. Yeah, so long range tasks. Existing vanilla GNNs, they're not very efficient on that. If you plug in some graph transformers with any sort of positional features, they start working much better. And that's a still pretty big area of research. We haven't seen many papers that would beat GPS on LRGB. So that is still pretty exciting to see what folks come up with. And GPS++ won the large-scale challenge. It was a collaboration with Graphcore, with the UK hardware startup. And that was a pretty dope version of GPS with an ensemble of 100 models. They had a lot of compute with applied on training tricks for that. And yeah, that was a big Christmas present for us, knowing that we won the whole challenge. Actually, the guys were pretty non-believing because they were announcing, OGB folks were announcing results week by week. And first they announced third place, then second place, and folks started, no, we're not winning. So now, guys, you gotta believe, And then we ended up winning the challenge. Yeah, so there will be actually a new ongoing challenge is already there. We are not there, but we'll be looking at the numbers. Who will be better than those ones, or for the private domain. So yeah, graph transformers or all the rage. That's how I entered the world of AI for science and molecular modeling as well. So if you look at it as a foundation model, does it qualify? That's a big question. So generally, the data sets there are still pretty small. However, a PCQM is large enough. So it only have 4 million points, but it contains a lot of elements from the periodic table. So you can use it as a pre-training for other tasks. So some other graph classification data sets, I think this will PCBA. Pretty much all the models you see in the top, they have been pre-trained on PCQM. PCQM is small though, and it's not wide enough, say, to be applied to protein tasks. So it's only for molecular tasks. It raises an important question: how much data is generally there? Because if you look at the LLM world, well, you have the pile Reddit, GitHub, and all other data sets. We leave apart from here the questions about copyright and how good or bad was to scrape all those data sets and feed them to LLM. Like rumors are that modern LLMs will be trained only on copyrighted data. So yeah, there are enormous LLM datasets, and there are pretty small scientific datasets. That is still a problem for AI for science models. Perhaps the biggest one, answering how much data is there in general, that's a pretty recent release that the paper appeared on the NeurIPS data science and benchmarking track. It will be this year. It's the model with about 100 million molecules and about 13 billion labels. This one comprises actually PCQM with some additional data, and also contains some quantum mechanical labels like in DFT simulations and other stuff as well. So overall, it will have something like 100 million molecules, maybe 1 billion conformers, 3D conformers. So that will be some 3D data and some classification and regression labels. Is it good? Is it large enough? We don't know, because there hadn't been any model trained on it yet so far. And another question: what is the pre-training objective? So next token prediction for autoregressive transformers is cool. Can we derive something similar for AI for science applications? there has been quite some struggle with that, I would say. One of the techniques is doing sort of denoising out encoder, pretty much what Bert did, but for 3D coordinates. I think it's so far one of the most promising ones. It's called noisy nodes. That if you have 3D coordinates for your 3 input, then the molecules or crystals or something, you just add some Gaussian noise, and you try to predict a new one. We tried it for GPS plus, didn't work at all, but in other models, actually bumped the performance. So one potential candidate, but surely not as universal as next token prediction. If you work with string representations of molecules or crystals and other structures, then you can start with their string representations. That will be some smiles for molecules or selfies or some other textual descriptors, and you can slap your favorite transformer on top of that as well. And you can derive some scaling laws. So that was a relatively recent paper from last year, how you can scale those CAM GPT. Well, proteins, for instance, all the protein LLMs work in the domain because proteins are only represented with the textual sequences. If you dig a little deeper, then you can start thinking maybe we should think about energy structures, about energy properties and some equilibrium structures. And that's the task taken by a recent distributional performer from MSR. So their input is some 3D structures, can be anything from protein to crystals. And the output would be equilibrium energy distribution. And a byproduct, it gives a nice diffusion generative model. So having some input descriptors, which can be like texts or 3D information or some lattice for crystals, you would train a model which would predict equilibrium distribution. So those are some essentially energy states where the structures are stable and have some nice properties. And usually stable structures, they have minimum and potential energy surface. So the lower the energy. In the proteins, yes, string representations are still the best. And very nice observation is that if you train a protein model, here is ESM2, evolutionary scale modeling, pretty much the state of the art in any protein, a lot of protein models that you would see publishing right now. It is doing simple mask language modeling on protein sequences, but folks have found that if you look at the representations, you will see that it actually has some notion of the 3D structure. So even though you only feed a sequence of 20 tokens, 20 different types of tokens, you'll see that the weights of the transformer, they will start having some notion of the 3D structure. That's a pretty cool result. That's actually the sign of some emerging capabilities of those large models in the protein area. And ESM2 is being used in quite a number of state-of-the-art models like DivDoc. DivDoc is the diffusion model for protein ligand docking. And then ProtestT, that's actually the work that Intel has done with Mila. This is a text-to-protein retrieval. A few words on ProtestT, which was another chain, it's the model for pre-training on joint training on biomedical text and protein sequences. So it's essentially what you can do is that you can type that I want to get this protein with certain properties, and it would retrieve that from the set of known ones. And for that, they built quite a huge data set of pairs, where I think a few million, where proteins will have some textual descriptions. You do some clip-like objective. So it's sort of a clip, but for proteins and text instead of images and text. And another interesting area we'll be investing quite some efforts will be MD simulations, molecular dynamics, because that can be applied to all those molecules and 3D structures as well. It has a lot of names, null potentials, force fields, and the main task is to predict how the structure changes over time. So all those fancy GIFs they're actually showing that your molecule, the one that with some 3D structure, is actually changing over time. And it's of higher importance for any drug design, because if you're thinking about how ligand attaches to protein and you actually want to simulate it in certain nanoseconds or milliseconds to learn how it actually attaches. and it's applied. It can be applied through some DFT simulations to all those structures. The problem is that it is slow and expensive, and the silver bullet is not yet there. However, some models try to approximate that with the ML models, so that is still of huge importance. It's pretty hard to do, but the potential benefits from it are pretty big. Yeah, going back to materials and crystals, something we released recently, also submitted to New York's data science party, probably rejected from this track, and we still released a previous version at TMLR, journal. So that will be open multi-ML toolkit. So that is a huge library for doing all stuff crystal ML, working with crystal. So we accumulated quite some number of data sets with 1.5 million materials. That's tiny compared to LLMs and compared to all those huge molecular data sets, but it's still the biggest collection of materials that you can work on right now. We have several baseline models, even some generative model, pretty basic one, but still diffusion-based model. And we'll be experimenting more, trying to building a nice representation learning model on those 1.5 million materials for that. The data sets here, apart from Open Catalyst probably you might have heard of it. It's the flagship thing from Thayer, from Meta, from AI for Science initiative, and it's for MD as well, but it only covers subset of bulk materials. And if you look at we'll be interested to look more at some other structures like LIPS, Nomad, or OQMV, and that's still not that large, but still a nice collection of data sets and tasks. So, for instance, what no one hadn't tried yet to do is to train multitask models. Would your model learn good representations if you train it on energy and forces and property at the same time? So that is surprisingly still a question because no one has tried that. But generally, the world of crystals, as we see, is not as large as molecules, simply because I think pharma is behind all those molecular ML. They're pouring a lot of money into that. And for crystals, there are some inherent problems, and it's not on that scale yet, but we're trying to get there. So some open challenges and potential projects will be interesting to work on is designing such a huge model that would capture all the variety of those millions of materials because of their dramatically different properties. Some of them are very small, like 2-3 atom materials, but periodic structures, so they're infinite crystals, or they can be huge compositions of 50 or more. So that is still the problem. We don't know what will be the best training strategy. I would like to improve physics-informed generative models. So here we talk about diffusion models, flow matching models. The flow matching models will be everywhere next year. And run some MD simulations, physics-informed GNN. Should be physics-informed GNN, not GNN-informed. Yeah, to do some simulations of those. And yeah, that will be it so far. So if you have some interest in those, just drop us an email, and yeah, we'll be happy to do. Yeah, I'm on time. Thank you. Can we get the slides from Zoom? Yes, we'll be sending the slides. Yeah.
And that was for reintegration and classification. But in the later data science, you for graph information for the foundation models. So I wonder if you have any information on what kind of filter foundation model should I talk with in the past or the data transpose when they're for the designing these TILOS?
Yeah. The answer has something to do with the graph theory. So generally, link prediction tasks are harder because of symmetries that you have in a graph. So if you have very irregular structures, say with rings, or some other highly periodic structures, a lot of nodes if applying vanilla GNNs, would look exactly the same. So they'll be indistinguishable. For link prediction is particularly of higher importance. For node level tasks, graph level tasks like graph classification and something else, there are some methods that would go higher orders. Actually, graph transform is a second order method. That would already will be sort of considered as a 3WL theory of expressive power. So graph transformers are good for node and graph level tasks, still not good for link level tasks. That is still a problem in the community, and there has been quite some research on that, trying to understand if we have expressive node level, graph level model, will it work as well for link level tasks? So far, the answer is no, and it's still unsolved gap.
So for this kind of molecular data, in fact, both for the knowledge graph and the link, you may have, data for may carry important information or other motifs.
I'll be repeating the question. So the question was about importance of higher order structures in molecules and proteins and crystals. It is important because especially crystals, they are periodic. So if you would apply blindly GNNs, it won't work. You would need some things to break the symmetry. So higher order structures, essentially their task is to break the symmetry. And whatever helps to break the symmetry is good. So higher order structure is good. They are expensive though. So far, what we can scale at most will be transformers. And I think beyond transformers is already practically not applicable if you have large amounts of data. Then we're entering all this area of efficient transformers and what folks have been doing with LLMs for a few years already. That will be quite engineeringly heavy. So if there is any other method of breaking those symmetries, that will be even better. So far, higher order structures like pairwise connections. That's something which is the main building block of those. There are some more exotic models that would go for, say, 3 tuples or more, actually, or infinite GNNs. They are on the level of nice papers on Europe, or SELR, and with a little practical implementation. A question from the chat. In the relation graph that you constructed, what did the edges represent? Yeah, going back to that. So edges in the relation graph here would be representing 4 fundamental interactions between relations. So those are 4 of them, like head-to-head, tail-to-head, and so on. And they are built efficiently from the original graph. So and they are pretty generic for any multi-relational graph, because tails and heads, it's something that we define from the adjacency matrix. And we can derive this graph of relations for any multi-relational graph. So the edge types, there are only 4 of them, and those 4 are transferred for any possible multi-relational graph.
So any of these these code that you talk about, are these open source, or you have constructed it?
You mean the code? Or?
Yeah, the code to derive relations, is it applicable for any graph that we can use?
It is, yeah. It's just for sparse matrix multiplication. So that's, that's pretty straightforward. In terms of publishing the code, we'll be publishing it perhaps next week. I'm polishing up some pipelines there, but the archive is there. So all the formulas, how we build it, are there. And just one sparse MM for each of the relation types. The code will be there in a week or 2.
Awesome. Thank you.
Sure.